Welcome. So this is a quick tutorial on performing cluster analysis in RapidMiner. And to begin with, for this example process, we're going to be using a data set, which is a famous data set called Iris. And let's have a look at it. So I've just pulled this data set into our process view. Let's run it and see what it looks like. Well, here we go. We have a bunch of different variables that relate to flowers. Specifically, we have the species listed here as our label. And as a matter of fact, let's first go into the statistics overview. And here we'll get a good overview of what we're dealing with. We have data on, let's see, 3 different kinds of flower species: setosa, versicolor, and virginica. Okay, we have 50 observations of each, so it's a pretty balanced data set. And describing these 3 different species, we have some features on their sepal length, on their sepal width, on their petal length, and on their petal width. And so we don't have any missing data here. We see that we have different average values, min, maxes. We won't go further into this data for now. Let's just go back to the overview here. So this is what we have. What we're going to try and do today is basically disregard the species itself, and we're going to try and find commonalities of different groups of flowers, pretending that we wouldn't know what species these observations belong to, based entirely on sepal length, sepal width, petal length, and petal width. So we're going to try and find some groups, some clusters in this data of 150 observations. Okay? How do we do this? Okay, so first thing we want to do is we're going to go back here into the design view, and something we always want to do when we work with cluster analysis or any other method, in fact, that works with distances, is we want to normalize our data. The reason for why we do this is if let's go back for a second into our data. If we don't actually normalize our data, then we implicitly give a lot more weight when carrying out the cluster analysis to those variables that are measured on a much larger scale. So for instance, here we can see, if we look at these different variables, the min, max, average values, if we click on them, we get the standard deviations. It seems that, for instance, petal length would overly influence our results simply because it is measured on the largest scale. So we also see the largest standard deviation here. And that's something we don't want to do. We don't want petal length to over-influence our clustering results, to be given undue weight when it comes to creating clusters. We want to have a level playing field and all of these different attributes to be able to contribute equally to finding out commonalities or clusters. And so for that reason, we go back and we normalize. What we do here is we provide our data to the normalize operator, and everything else we leave here as standard. We use a Z transformation, so basically we subtract the mean or average of each of the different attributes or variables divided by the standard deviation. And doing so, we get a nice normalized attribute or variable that will then have a mean of 0 and a standard deviation of 1. So let's do that, and let's add a break operator here to see what's going on. So breakpoint after getting the data. First we run, we get the data, we see all of these are still in their original scales. And now we normalize, and as you see, everything here now is expressed in standard units. which means it's much harder for us to interpret. The only thing we can now say if some observation has a value of 1.245 is that this particular observation has a sepal width that is much larger than the average, which would correspond to a 0, such as this one, for instance, close to 0. So anything below 0 is smaller than average, anything above 0 is bigger than average. That's as far as what we can infer now based on these values. But we have, if we go into statistics and we look at this, we have our equal playing field here now, averages of 0, standard deviations of 1. So after we've now normalized our data, we would like to run the clustering algorithm to be able to find groups. Now if we look for cluster operators here, there's a bunch of different clustering approaches. The one that we'll use is just a simple k-means approach, so we'll drag this in here. And really the only thing that we'll do here for now is play around with different values for k, meaning the different values for those initial centroid seeds as well as our cluster numbers. So if we provide a value of 2 for k, it will look for 2 clusters or 2 groups. So we can start with that to see what happens, and everything else here we'll leave as is. So let's run this. We can remove this breakpoint, and we get our clustering solution. So as we've said, we asked for k equals 2 clusters, and so we get cluster 1, which computer science denotes as 0. Different way of counting, cluster 1 and cluster 2, or cluster 0 and cluster 1, 50 items in one, 100 items in the other. So we have 2 different groups. If we go to folder view, this won't be of much use for us. We actually see which observations are in which clusters. We're going to skip to the centroid table. This is really interesting. What does this tell us? So here we have the different attributes, the different variables that we've talked about that we were going to use to find different groups of flowers that shouldn't say behave, but that have similar features. And we have 2 different clusters. These are centroids that we're showing here, and what that means is that after the final convergence of allocating all these different observations to 2 different clusters, those were our final centroids. Meaning that at cluster 0, the centroid for sepal length is at negative 1.01. Meaning that, again, because these are standard units now, all we can say is that cluster 0 compared to cluster 1 is very small when it comes to sepal length. So sepal length is smaller than average for cluster 0, whereas for cluster 1 it's slightly above average. And so we can compare the others for sepal width. We know that cluster 0 has sepal widths that are slightly larger than average, and cluster 1 has sepal widths that are slightly lower than average. For petal length, similar story. Petal width, similar story. So we have some striking differences here in terms of the 2 different clusters and what their centroids look like with regards to these different variables. So we can use this to describe these different clusters, really. Something else that we want to look at, which is really the same thing but just expressed in the plot, is looking at those centroids on the plot. And what we see here is we have 0 and 1, blue and red, and we have the different attributes down here, and what we see on the plot are the different centroid values. And so similar to what we just did before, we could describe and say, well, in terms of differences, the first cluster has a much greater sepal length, a smaller sepal width, a greater petal length, and a greater petal width, compared to cluster 0, which is our blue line here. Okay, so far so good. We found 2 clusters, or rather we asked for 2 clusters. An obvious question now is, so how do we choose between different Ks, between different amounts of clusters? We can set any given value of K and try and see what happens. That's not necessarily an approach that you might be comfortable with. You're going to ask yourself, but what's the optimal K? Can't we sort of optimize this or find a correct value for K? Well, for our class, we're really going to make this dependent entirely on interpretability and practical usage. So the amount of clusters will depend on what use we will have for them. Meaning that if we're talking about groups of customers, for instance, how many different groups can we cater to? How many different groups are useful when it comes to distinguish different groups? If we start distinguishing groups on very small details, it might not really be worth to have 2 separate clusters for small details. Okay, but in this case, we're dealing with different groups of flowers, and so we want to get an idea of whether we can do any better. And if we're starting to talk about better and worse, one thing we can do, and we'll use that, is also just looking for all these cluster operators. Down here we get a performance measure for clustering, and the one we're going to use is cluster distance performance. Cluster distance performance basically asks for basically the cluster model as well as the clustering example set. Okay, so we get both from our clustering operator here. Once we connected those, what it's asking us for is what do we want to use as our main criterion, and we're just going to leave it as average within centroid distance. What does that mean? It means it gives us an idea of how cohesive our different clusters are. Average within centroid distance relates to how far all of these different observations within the different clusters are to their centroids. And what we want to do is minimize that distance, right, to have more cohesive clusters. Now, everything else we'll leave as is. And let's run it. We haven't changed anything else. The only thing we've asked for is this performance measure. Let's see what it provides us with. Okay, so now we get this performance measure. I should go back and also actually connect our clustering solution here. Let's run this again. Okay, so we had this before. We were looking at this just now. What we get additionally now through the performance operator is this performance vector. And what this provides are different distance performance measures, starting with the overall average within centroid distance, which is given here as negative 1.4, which on its own right now for us is hard to make any judgment calls on, because we don't have anything yet to compare this to. But we have our 2 clusters that we asked for, cluster 0 and cluster 1, and what we also get here is the average within centroid distance cluster 0 and the average within centroid distance for cluster 1. Clearly, one thing we can already say is that cluster 1 seems much less cohesive. There are observations with regards to cluster 1 that are further away from the cluster centroid compared to cluster 0. Okay, it has a smaller average within centroid distance. And overall, this is our average within centroid distance. And what we can do now is actually go and ask for a different set of clusters. So instead of 2, let's ask for 3. Okay? And we're going to run it. And now we're going to get 3 different clusters. Cluster 0, cluster 1, cluster 2, almost neatly balanced. Again, remember that we're going to pretend that we don't actually know what these different observations, which species they belong to. But it seems we're getting at that, even though we have to check whether this is actually correct. But that's not something we're concerned with right now. What we want to do first, as usual, is, well, let's look at our centroids. So here, they still nicely distinguish the three different clusters with respect to these different attributes. So they really are all pretty far away from each other. There's some mid values and then some positive and negative extremes. Okay, we look at our plot, which is the same thing again visually. Maybe it's easier to interpret. And we have three groups, clearly with the red and the blue sort of repeating patterns, but at different absolute levels. So the blue group of species or blue group of flowers that we have now grouped together here in cluster 0 tend to have, well, everything sort of the biggest and largest and longest. So longest sepal length, longest sepal width, longest petal length, and longest petal width. Actually, I am sorry, with the exception for sepal width, in which the max belongs to cluster 1. Now, that seems like we can still distinguish these three clusters nicely, and so from an interpretability perspective, we could go ahead and use three clusters if we believe it helps us better distinguish between groups and observations. What we have now, however, is also this comparison of distance performance measures. And to begin with, if you recall, previously our average within centroid distance overall was about negative 1.5. We've decreased that substantially. What does that mean? Well, it tells us that our three clusters, on average, are more cohesive than our two clusters, which is good news. And if we look at the respective clusters, we see here for the first cluster, a negative 0.9, second cluster negative 0.9, third cluster negative 0.8. So all pretty cohesive. Before also we had one of them at negative 0.1 or so, I believe. So that's good news. So we seem to do better with three clusters. Okay. Now if we go back to our model here, we could now proceed and try out different amounts of K for a different amount of cluster solutions, and I encourage you to just plug and play and try out different ones and see what happens to both the individual clusters as well as the different distance measures for within clusters, cluster 1, 2, 3, or 4, let's say if you ask for 4, as well as the average overall within cluster distance, which we want to minimize. But remember, minimize only as long as we believe that this is still an interpretable and useful. And when I say useful, I mean managerially relevant solution for a problem, meaning we have clusters that we can target and not just a meaningless high amount of clusters that are only described by very small differences. That's not something that's that useful for us in practice. The last thing we can do is we can actually, here from the performance operator, ask for that example set, and it should, let's run this again. It gives us now additionally this example set, which actually saves the cluster membership for each of these observations. Okay, something we could do now is we could compare this to the species to see if we did a good job in clustering these three different species into three different groups, but that's not something that I'll do for now. That's something you can try out yourself. But the idea here was simply to walk through a simple iteration of a clustering algorithm, applying it to a data set within which we were interested to establish patterns to try and find common groups that behave or have similar features. and then try and find the optimal number, again, based mainly on interpretability, but if we want to use a performance measure, we can go by average within centroid distances to decide on how many clusters, in this case set by k, we would like to extract and work with.